Okay, hi everyone, welcome to lecture 10. And today we're going to talk about the fundamental theorem of Markov chains, and we're going to prove it. And we're also going to talk about PageRank, which is a cool application of all of this that we're talking about. Okay, so, all right. So the outline of the talk will be, of the lecture today will be that in the first part, we're going to talk about the main tools that we'll need to prove like the main kind of mathematical theorem that underlies Markov chains, which is the Perron-Frobenius theorem. And then we're going to see as an application of Perron-Frobenius, like the fundamental theorem of Markov chains, and then we're going to talk about PageRank. Okay. So, all right, let's get started. So first, let's just recall some, linear algebra that we'll need for this class, right? So if I'm given a square matrix A, okay, let's say this matrix is like just real, has real entries and is an n by n matrix. We say that lambda is a complex number, is an eigenvalue of A if there is a vector, a complex vector such that, when I multiply A by V, I get lambda times V. Okay, so that's the definition of an eigenvalue, right? And V is the eigenvector, right? So we would say that V is the eigenvector, and maybe let me write it here. So V is an eigenvector corresponding to lambda, right? So, all right. And now we can define, once we know what eigenvalues are, right? So we can define the spectral radius of a matrix A, which we denote by rho of A, okay, is the maximum of the absolute values of the eigenvalues of A. So, if you're going to write this, you write rho of A, you can just take as maximum over lambda eigenvalue of A of the absolute value of lambda. Okay. So this is the spectral radius of a matrix A. And then we have that, which is just not a hard theorem to prove, that, Gelfand's formula, it just holds that if you have any matrix norm, okay, here I put the Frobenius norm, like there's the F here, and this Frobenius norm of a matrix, okay, is nothing more than like the trace of A transpose A. You take the square root. Okay, so this is a norm, but Gelfand's formula is more general, but here I don't care. I'm just going to use one of them. So if you take this norm, which is the Frobenius norm, you can compute the spectral radius of A simply by taking the limit of, you take the matrix A, take it to the, oh, yeah, so this n is different from the other n. Yeah, so maybe let me say like t going to infinity here, I have 1 over, like t 1 over t. So I take a matrix A, I power it to some power t, then I compute the Frobenius norm of this power, and then I take the tth root of this matrix, right? And this will be equal to my spectral radius, okay? So this is just a formula that we'll need. And all right, and here, another thing that we should note is the concept of geometric multiplicity, okay, of an eigenvalue. So what is the geometric multiplicity? So we say that an eigenvalue lambda of a matrix A has geometric multiplicity K if you take all the eigenvectors of A with eigenvalue lambda, this space will have dimension K. Okay, so in particular is equivalent to the dimension of the null space of this matrix to be K. Okay, so let me just give a simple example of this, right? Like, which is very, very simple. So if I have a matrix A, which is the following matrix, like 1, 1, 0, oh, sorry, 1, 1, 2, let's say, right? So this matrix clearly has two eigenvalues, right? Like the eigenvalues are 1 and 2, correct? Now, what is the geometric multiplicity? So the geometric multiplicity of one of the eigenvalue 1 is exactly 2. because maybe let me put 3 here just so that this 2 does not become like confusing, right? So the geometric multiplicity of 1 is actually 2. And why is that? Because we have that any vector of the sort alpha E1 plus beta E2 is an eigenvector of 1, right? So and there's no more, like this is the biggest space, right? So if I add E3, I don't get an eigenvalue of 1 anymore, right? Because E3 gets multiplied by 3 times its value. Okay, so it turns out that here the geometric multiplicity of 1 is 2 because I only have this 2-dimensional subspace. Does that make sense? Okay, so and then like after the geometric multiplicity, okay, we also have the algebraic multiplicity. Okay, and then those can be different, as we're going to see in an example now. So the algebraic multiplicity of an eigenvalue is just like the largest power of like t minus lambda that divides the determinant of t times identity minus a, right? If you remember, this is the characteristic polynomial. Characteristic polynomial of a, right? So this is just the characteristic polynomial. This is a polynomial. This is a univariate polynomial, right, in the variable t. And if you look at the root, so any eigenvalue is a root of this polynomial, right? But now, if you look at the multiplicity of this root of the characteristic polynomial, this gives you exactly the algebraic multiplicity. Okay, so for example, if we have the matrix, again, let's just look at the matrix 1, 1, 3. If I take the characteristic polynomial, what do I get? It's exactly the polynomial t minus 1 squared times t minus 3. And then we can see in this case that the algebraic multiplicity is also 2 of 1, right? The algebraic multiplicity of 1 is also 2. But now you may ask, well, okay, well, are those concepts like always the same? And the answer is no, because here's a very simple example. And this comes because, you know, you have the Jordan normal form, right? So that's why we have those things. Look at this matrix A, which is just the matrix 1, 1, 0, 1. Okay. So what are the eigenvalues of this matrix? Well, if you compute the characteristic polynomial, the characteristic polynomial is exactly t minus 1 squared. So in particular, we know that the algebraic multiplicity of 1 is 2, right? But the thing is, like A only has one eigenvector, which is E1, right? And the eigenvalue is 1 here. So the eigenvalue is 1. Therefore, the geometric multiplicity is 1. Does that make sense? Okay, great. So then this is just like, these are just some concepts, and you don't need to worry too much about them, okay? Because like I'm just talking about this multiplicities just so that you know kind of the full statement of the Perron-Frobenius theorem, but they're not going to enter our course in any significant way, okay? So, all right. So, and then, well, I guess I did the example before the slide with the example, right? So that was the example that the algebraic multiplicity can be different from the geometric multiplicity, okay? So these are the concepts that we're going to need. And also we need a positivity lemma, okay? And this is just something that will work for positive matrices, okay? Now, what is a positive matrix? So we say that A is a positive matrix if every entry Aij is bigger than 0, like strictly bigger than 0, okay? So this is a positive matrix. So here is the lemma that we need, is if A is a positive matrix and U and V are distinct vectors such that U is greater or equal to V. And what do I mean by U greater or equal to V? So U greater or equal to V if and only if each coordinate we have UI greater or equal than VI. Okay, for each coordinate. Then, so if we have U and V, they're distinct vectors such that U is greater or equal to V, which means that for, some coordinates could be equal, but there is one of them that will be different, right? Because they're distinct vectors. Then we know that A times U is bigger than A times V, right? Moreover, we know that there is an epsilon bigger than 0 such that, A times U is bigger than 1 plus epsilon times A times V, right? So let's just prove this lemma now. It's nothing really hard, right? So just note that if we're trying to compare, like we're trying to prove this, right? That AU is bigger than AV. So we might as well just, try to prove that A times U minus V is bigger than 0, right? Because that's equivalent. So, all right. So note now, so let's just compute A times U minus V. If we compute this, right, just note that, okay, sorry, okay, I did something wrong here. So let me just do this. Like, let me take AU minus V, and let's compute just the ith coordinate here. Just the ith coordinate, okay? So in particular, what happens, sorry for the typo here, this will be what? This will be exactly the sum over all j's, over all index j's, right? Because I'm just taking the ith row of the matrix A and multiplying by uj minus vj. Does that make sense? Okay, so then the ith entry of this vector, right? Because I have a matrix multiplied by a vector. So the ith entry of this vector is equal to the sum, which is greater than or equal. And now here, I can just say, you know what? From all these aij's, I will substitute them by the minimum of the aij's, right? And we know, so what do we know? We know that these guys are non-negative. So if I decrease aij, the value of aij, I'm just decreasing the total value of the sum. Does that make sense? So then I can replace all of these aij's by the minimum entry of my matrix times, and then all I'm left with is the sum of the differences, uj minus vj. Does that make sense? Okay, great. But now, what do we have, right? So let me just correct this slide as well so that it's properly written. So the thing is, since we know that uj is greater or equal to vj for all j, and u and v are distinct, implies that there is one index that this must be a full inequality, right? So in particular, we have that this sum here, right, is greater than or equal than uk minus vk, which is bigger, strictly bigger than 0. So in particular, we know that each entry here of like au minus v, right, is greater or equal to this, which is like, which is bigger than the min of aij times some number, like, let's say mu or something, right? But this is bigger than 0. So this is strictly bigger than 0. So then we just proved that for each coordinate of this matrix, so what did we prove? We proved that each coordinate of this matrix, if I take the ith coordinate, we proved that all the coordinates are bigger than 0. Right? And in particular, not only we proved that, but we proved that, if we take this like uk minus vk here, right? Like we proved that this is less than mu times the minimum entry aij, right? So there is this kind of constant that is there. So, all right, so then what do we do, right? So now the moreover part, there exists epsilon. You can just take epsilon to be, like small enough compared to this quantity that we talked about. Right? Then, if you take epsilon really small, you obtain that like AU is actually like bigger than 1 plus epsilon times AV. Okay? Does that make sense? Is this positivity lemma clear? Okay, great. So, all right. And the important thing to notice is that epsilon just depended here on my matrix A and my vectors U and V, right? That's it. Right, I just need to choose epsilon like small enough, but it depends only on A, U, and V. Right? Okay, great. So now that we have the background, like the linear algebra background we need, we're ready to talk about the Perron-Frobenius theorem. So